All right, so this lecture is on what are called the alternative gas laws. That's kind of a not necessarily the most correct name in the world. Basically, these are relationships between, say, only pressure and volume that you can get. We can actually derive them directly from the ideal gas equation. Historically, these actually were founded first, and then they were assembled into this ideal gas equation. Um, but since we've already learned the ideal gas equation, the easiest thing is to have that PV equals nRT memorized, and then you can easily get all these different alternative gas laws from that equation. So let me show you what I mean. Okay, so there's three that we're going to talk about: Boyles Law, Charles Law, and Avogadros Law. Boyles Law is the relationship between volume and pressure when the number of moles of gas and the temperature of the gas are held constant. Charles' law is a relationship between the volume and the temperature of the gas when you hold constant the number of moles and the pressure. And Avogadros' law is the relationship between the volume and the number of moles of gas when you hold pressure and temperature constant. Okay. Actually, I'm going to do something a little last minute change here. I'm going to actually do Avogadros' law first because I think that one's maybe the most intuitive, the easiest to understand. So let me skip down to that. So again, Avogadros' law is the relationship between volume and number of moles when you hold the pressure and the temperature constant, right? So these are always before and after type problems. What happens to volume and number of moles before and after, some sort of a change. But the key here is that pressure and temperature aren't going to change from before and after. They're the same, okay? So let me show you what we do. So since we know that Avogadros' law is the relationship between volume and number of moles, what we're going to do is, well, and so first actually, let's just look at like what we're mean here, okay? So this is a depiction here of the volume that's occupied by a certain gas. And again, the pressure is going to be constant here. All right, so let's say that I have 1 mole of gas in this container here. Oh, I guess we should be moving here. 1 mole of gas in this container. So 1 mole of gas. If I increase the number of the moles of gas in that container, right? So I double it to 2 moles. I'll also double the volume. Okay, and again, this is at constant pressure, so the pressure isn't changing here. Likewise, if I remove the number of moles of gas, so I go from being 1 mole of gas to half a mole of gas, I'm going to decrease the volume. I'm going to cut that in half. Okay, so it's fairly intuitive to think about. Basically, if you're adding gas to a container, as long as the pressure is variable, you'll increase the size of that container. Okay, so in this case, this container has this little valve that can move up and down in order to keep pressure constant. So that's what's happening here. You can another example would be if you had a balloon, right? How do you blow up a balloon? So you take a breath into it, it gets to be a certain size. When you take another breath, you've added more moles of gas and you've increased the volume of that container as well. Okay, and that's because the pressure of that balloon is constant. Okay, so a balloon is actually a constant pressure system. If you tried to increase the pressure of the gas inside, the balloon would just expand. So this is a fairly intuitive concept. Basically, if you have a constant pressure and a constant temperature, increasing the number of moles of a gas will increase its volume. Okay, so let me show you mathematically, because this is what this chapter is all about, are these mathematical relationships. How do I get the relationship between volume and number of moles? Again, we're going to start with PV equals nRT. Everything in this lecture is going to revolve around you having memorized that formula. What we're going to do is, these are our variables. Right? That's Avogadros' law, is the relationship between volume and number of moles. Everything else is constant. R is always constant. And in this particular example, temperature and pressure are constant. So what you're going to do is you're going to put all your constants on one side of the equation and all your variables on the other side of the equation. So let's first move our constants to the right. So in this case, I'm going to divide both sides by pressure. All right. That will cancel pressure on the left. And now I'm going to move my variables to the left side of the equation. So I'm going to divide both sides by n. And that allows me, let me color code here. So this is my n, this is my n. So that allows me to cancel number of moles on this side. So what I'm left with is volume divided by n equals RT over P. Okay. And again, everything on this side of the equation, these are my variables. That's what I'm coloring in red here. And everything that I haven't colored are constant. Okay, so that means that if I took this equation for before, which we mark by 1, so V1 and N1 really means the volume and the number of moles before, and then I did the same thing with the equation for after, where volume and number of moles, so after I'm going to use this subscript 2, well, again, this is constant, and this is constant, and they haven't changed throughout the experiment, so they're the same exact thing. So that's how we get this relationship, V1 over N1 equals V2 over N2. Right, so move everything that's a variable to one side of the equation, and that gives you your before and after relationship. So it's not volume times number of moles, it's volume divided by number of moles. And again, I got that by rearranging that ideal gas equation. Okay, I put everything that's constant over on one side, and so the whole idea is everything in blue here is the same both before and after I make this change. So for example, taking that breath into the balloon, if the pressure and the volume, the pressure and the temperature were the same before and after I breathed that extra breath into the room, the value of everything in blue here would be the same, which is why I can set V1 over N1 equal to V2 over N2. And this is Avogadros Law. Okay, there's 3 of them. Boyles, Charles, Avogadros. If you want to memorize them and that makes it easier for you, go for it, because there's not that many of them. I dislike memorization wholeheartedly, and I think it's easier for me to understand if I can see how to get them from the ideal gas equation. So that's how I'm going to teach it. But again, if you just want to memorize that this is Avogadros Law, V1 over N1 equals V2 over N2, go for it. That's, different people find different things easier. Again, I'm not a memorization guy, so I like to know how it was derived, and this is how it's derived, okay? But then we can use this relationship here to answer before and after type problems. So what do I mean by that? So now we have this equation, V1 over N1 equals V2 over N2. So let's see an example of how that would be used, okay? I have 1.5 moles of an ideal gas that occupies 10 liters under a certain temperature and pressure, which again are going to be held constant. Determine the volume that 3 moles of that ideal gas would occupy under the same conditions, right? So that means beforehand, my volume's 10 liters and my number of moles is 1.5. And then afterwards, the number of moles is 3 moles. So how do I figure out the volume after the fact, right? So again, number of moles before is N1. The volume before is 10 liters. I know the number of moles afterwards is 3 moles. So what I'm looking to solve is that missing variable V2. So I'm going to rearrange this equation by multiplying both sides by N2. So I get V1 over N1 times N2 would give me V2. Right, and again, just to kind of color code what's what here, so we can see how these variables fit in to what's given in the problem. we see that the only thing we're missing here is that last volume, right? And so again, like you could think about this as you took a breath into a balloon and you breathed in 1.5 moles of gas and that balloon was 10 liters. What if you took another breath and there were now 3 moles of gas in that balloon? What would be the volume of the balloon then? So we can just plug in our variables here, 10.0 liters divided by number of moles before is 1.50 moles times the number of moles afterwards is 3.00 moles. Plug this into our calculator and we would just get 20. Okay. So 10 times 3 divided by 1.5 or 10 divided by 1.5 times 3, whichever way you did it, you would get the same answer, which would be 20. We're going to go through and make sure our units work. Moles cancel and we're left with units of liters, which is good because that's what I want, is a volume. That's right, V2, volume afterwards. And now sig figs, I'm gonna have to pay attention to. This number has 3 sig figs, this number has 3 sig figs, this number has 3 sig figs, which means that this number also needs to have 3 sig figs. So my final answer should be 20.0 liters. That would be the final volume. Okay, so we took the ideal gas equation, we arranged it in such a way that all the variables were on one side and all the constants were on the other side, and that's how we were able to obtain Avogadros law. All right. Boyles law is the relationship between volume and pressure when number of moles and temperature are held constant. So we're going to play the same game. We're going to take our ideal gas equation. We're going to identify what the variables are. In this case, whoops. In this case, it's pressure and volume. And all of our constants are on the other side. That's number of moles and temperature. And of course, R is always constant. In this case, we actually don't have to rearrange anything. It's already set, kind of easy for us. So that's the same both before and afterwards. And again, both before and after, everything in blue is constant, meaning it's the same value. I don't know if that number is 5 or 5 million. It doesn't really matter. It's the same before and after, which means that I can set P1 V1 equals to P2 V2. And again, if you just want to memorize this as Boyles law, go for it. I think it's easier to derive it from the ideal gas equation. But this is Boyles law. P1 V1 equals P2 V2. So the pressure times the volume before some change happens is equal to the pressure times the volume after that change has happened, as long as number of moles and temperature are held constant. Okay, so an example problem would be, let's say if you've ever gone scuba diving, you know that the volume of air in your lungs actually shrinks as you go down. So that's what this problem is here. If a skin diver takes a breath at the surface, which is standard pressure, remember standard pressure means 1 atm exactly, filling his lungs with 5.82 liters of air, what would the volume be if he dives to a depth where the pressure is higher at 1.92 atm? So again, we take our Boyles law, P1 V1 equals P2 V2. The pressure before is this standard pressure, so that's 1 atm, times the volume before, which is the 5.82 liters, right? So this was before he went and dove down. And this is going to be equal to the pressure afterwards, which is 1.92 atm, times the volume afterwards, which is my variable. I actually didn't rearrange this before plugging in the numbers, but we'll see, it doesn't really matter. Okay, it's all about solving for that missing variable, which in this case is V2. So I'm going to divide both sides by 1.92 ATM. On the left, or rather on the right, that cancels out, so I'm left with V2. Awesome. Now I can just plug everything into the calculator. So 1 times 5.82 divided by 1.92, and I get 3.03125. Go through and pay attention to units. ATM cancels out, and I'm left with liters. So that's great because I wanted a volume measurement. And now when I pay attention to sig figs, this one ATM kind of as written, it looks like it has 1 sig fig, but remember that we were talking about standard pressure, which is exact. So this is exact, meaning I'm going to ignore it. And this is 3 and this is 3. Your book is not very creative, and the lecture slides, at least given by the book, tend to prefer 3 sig figs. That's not always going to be the case. So 3.03 liters is the final volume, right? So you can see that as the pressure increased, the volume decreased, right? So this is what we would call an inverse relationship. If the pressure were doubled, the volume would actually be cut in half. But this would be my final answer here using Boyles Law. Right, and the last one is the relationship between volume and temperature. This is called Charles' Law. Just to illustrate this one real quick, if we had a balloon, which again we said was a constant pressure system, but we tied it off, meaning that the number of moles can't change, gas can't escape or be put into the balloon. We can illustrate Charles's law by, say, in this case, what they're doing in this picture is they took this balloon, they blew it up, and now they're dumping liquid nitrogen, which is incredibly, incredibly cold, onto that balloon. And you see it shrinks, right? So as the temperature decreases, the volume will decrease as well. You could actually do this at home if you blew up a balloon and then stuck it in the freezer. You would come back and you would see that the volume of that balloon has actually shrunk in the freezer because the temperature has decreased. Let's derive this equation mathematically. We're again going to start just like we did before, PV equals nRT. What's being varied is the volume and the temperature. The pressure and the number of moles, and of course R, are all being held constant. So then we want to isolate our constants onto one side. So this would cancel out pressure over here. We want to put our variables on the other side. So temperature would be nixed out over here. And we would get this relationship V over T equals NR over P. Again, these were being varied, and everything over here is being held constant. So that means before I make any change, it's whatever constant value it is. But also after I made the change, that NR over P would still be that same value. So Charles' law is V1 over T1 equals V2 over T2. Okay. So then how do we do this in a problem? V1 over T1 equals V2 over T2. That's what we just derived as Charles's law. So let's say that we have a sample of argon that's originally occupying 14.1 liters at 25 degrees Celsius, and then it's heated to 50 degrees Celsius at constant pressure. What's the new volume? So we have our volume before, our temperature before, and our temperature after. So we're going to solve for the volume afterwards. Now, we derived these from the ideal gas law. So there's an extra step that we have to do with this temperature. What is that? And that is to convert to Kelvin, okay? You cannot use the ideal gas law or any of these gas equations. Anytime you're talking about gas, make sure you convert to Kelvin. So for the T1, 25 plus 273.15 would give me 298.15. And again, I'm going to mark that sig fig. 273.15 is exact, so I'm not going to pay attention to that when I do sig figs. It's always going to depend on whatever the other number is, which is in this case 25. Likewise, let's see if I can fit it up here. T2 is 50 degrees Celsius, so plus 273.15. That would give me 323.15. Again, I'm going to mark that sig fig there. If you don't convert to Kelvin, you will not get the same answer. Your answer will not be correct. Okay, so you have to make sure to convert your temperature to Kelvin in order for this to work out. So now I'm just going to plug in my variables. I can rearrange this equation first. It doesn't really matter whether you do it before or after. Multiply by T2. It'll cancel out over here. So plug in my variables, 323.15, again marking that sig fig, times the volume of 14.6 liters divided by 298.15 Kelvin, again marked with 3 sig figs. Punch that into my calculator, I would get 15.8242. Go back and pay attention to units. Kelvin cancels out. I'm left with liters. That's great. That's what I want. And then all three of these values have 3 sig figs. That's why it's so important to pay attention to sig figs. Again, these lecture slides tend to default to 3 sig figs. That's not always going to be the case. So it would have been very important to note that these numbers here only have 3 sig figs. My volume does too, though, so that's not. So then 15.8 liters. So you can see that the argon sample expanded because you increased the temperature from 25 degrees Celsius to 50 degrees Celsius. And that is Charles' law.